So today we're going to do a summary on encoder and decoder, and we're going to go talk about comparator. Then we're going to do the tutorial. Let me do the outline here. Okay, the outline. Today we're going to do summary of decoder and encoder. Then we're going to do a comparator, and then we're going to do a parity checker, and all the gray code. Basically is lecture 3 lah, tutorial. Okay, then later we're going to go to tutorial 3. After that, we're going to go to lecture 4 tutorial. Okay. In the tutorial 3, we're going to do question 1 and question 2 only. Okay. The rest of the question 3 to 5, you do it yourself. All right, we discuss next week. Okay, submission is this Saturday, midnight submission. Okay. Then we're going to go through, explain about lecture 4. Okay. So this is our outline for today. We hope to finish within 1 hour plus. Okay. All right. So in the decoder, you have 3 to 8 decoder. In the encoder, you have 8 to 3 encoder. All right. So if it's an active low, there's 3 input that give you 8 combination. 2 to the power 3 is 8. So there's only one output. Only one output will be active. Right? So it's active low. That means that only one output is low, the rest is high. Okay? And YC versa. Right? Okay, in the encoder, is the opposite of decoder. Okay, it's the opposite of decoder. So meaning to say that you have 8 input, only one input is different. Okay? Only one input is different. Okay, the rest must be the same. Okay, then the output is let's say the input is let's say line 7 is different. Is high lah. Okay, then output will be 111. Okay, so what is the problem with this? The problem with this is that in the encoder, the input sometimes you cannot control. Cannot control the input. So there is a problem with it. Okay, sometimes in certain design you cannot control the input, especially if you let user to give you the input. Okay, so in this case, you will cause the encoder circuit to be confused. Right? So therefore, it gives rise to what you have is a parity encoder. Yeah. Any question so far on the decoder and encoder? Okay, because in the encoder, you got 8 input and only one is different. If you give the user to put in the input, chances are they might not do what you want. Okay, clear? Okay, submission, you submit all question 1 to question 5 lah. Okay. Okay, next thing is comparator. First we start with 2-bit, then 4-bit, then 8-bit. Okay, basically in any circuit you learn is built on top of each other. Okay, we reuse what you have learned. Okay, so you have this what you call exclusive OR gate. exclusive OR gate, if 2 bit is the same, it will give an output. So you want to build a comparator, what you need to do is that just put a inverter in front of the exclusive OR. Then it will become, if both of them are same, it will give you a 1. If this different, it will give you a 0. So in this case, in order for this to be same, 1 is an AND gate, isn't it? So this one has to be 1, and this one has to be 1. In order for this one to have 1, these two must be the same. Okay. So this is a basic building block for 2-bit comparator. Okay. Then you also have a the same thing. So if you compare the same, then it's the same. You compare different, then it will be different. Okay. So the first output is 1. The second output is 0. Okay. So you also have the circuit called 7485. Is a 4-bit magnitude comparator. It gives you 3 output, whether A is equals to B, A is bigger than B, or A is smaller than B. Okay. So you have 4 bits of input comparator. Magnitude comparator. Okay. It tells you whether it's the same or different. All right. Then you can also build. Okay. So over here, this is A, this is B. So 110 and 1100. So you can see here 3 0. So this is the most significant bit. Okay. So most significant bit, and B is this one. So A is, so this one will be high. This one will be high. Right? The rest will be low. Okay. This part will be high. Okay. Clear? You got to see the bit position here, the MSB and LSB. Okay. All right. Then the next thing, this is how you build the 8-bit comparator using 2 4-bit comparator. So this is the LSB, this is the MSB bit. All right. So you can see here A0 to A3, A4 to A7. So this is how the magnitude bits input output is connected to the input. Okay. All right. It's connected to here, and this will give you the result. Okay, this is the result. The output is the result. Okay. So which one is the input? Which one is the output? So you can see here, this is the output. This is the output. All right, from this chip. And then you can see here the output is get fed into this input. Okay, this one is ground. All right, so when it's put into ground, what's the value of the ground? 0. Means 0. Okay, ground is 0. Okay, this is 0. So all the value here is 0. So this is the input, this is the output. Then the output will come up here. Okay. All right. Okay. Any question? I hear some dotted sign. Okay. All right. Sometimes you can help yourself. All right. Tolong menolong. You help each other, not help yourself. Tolong menolong. Help each other. It will be good, and you speed up everything. Okay. So how does it relate to each other? This one. All right. Let's say on the MSB bit, on the MSB, A is A is bigger than B. So nothing. So this one will be vector. So it will be none. Okay. So then if A is less than B, so this one is also vector. How do you spell vector? Also is a done deal. It means that the MSB say is smaller or bigger than it's done deal. If it's A equals to B, then only you look at the LSB input. Okay? If the LSB output is A, then A. Okay? If the LSB output equals to provided MSB A equals to B. Okay? Right? So this two input will be fed into here. Okay? So this is the slightly tricky part in the 8-bit comparator. Okay? Okay. Any more question? No, Okay. This one, no need. Okay, teach you how to connect already in the diagram. So you connect straight already. Okay, from the diagram it's already shown. So there's no question asked. Okay, then you have what you call a code converter. Code converter is you have binary to gray, gray to binary, then BCD to SS3. Right? So these are some of the converter. Okay. So this is the decimal 0, 1, 2, 1, 2, 3 until 15. In the gray code is like this. So what is a gray code? In the gray code, only one bit can change at one time. And you want to cover all possible scenarios. So in this case, this is a K-map. K-map, this is how it looks like. 0, 1, 3, 2, correct? Then 4, 5, 7, 6, 12, 13, 15, 14, 8, 9, 11, 10. All right? So this is a K-map, okay? So then you have a gray code. The gray code will be 0, 1, 2, 3, 4, 5 in sequentially, okay? So with this, you can get what is the value of 15? The value of 15 is 10 decimal. So you can see the value of 15 is 8, man. The value of 15 is 8, man. Wait. It's supposed to be 10, not 8. It's supposed to be 10. 1000. There is something wrong here, okay? Wait a minute, let me see. The value of 8, this 12 is 10. So 12, what's the value of 8? Ten is 15. See, 10 is 15. Then 11 is what? 11 is 10 is 15. 10 is 15. Then 11 will be 14. 11 will be 14. Okay. Then 12 will be 10. 12 will be 10. There is something wrong with this one. Okay. Something wrong with this one. Okay. So, but you remember from here, there's only one bit changes, okay, in the gray code. There's only one bit changes at one time. Okay. All right. There's something wrong here. Maybe it's like this. 16, 14. Seven is what? What is 7? 7 is 4. 7 is 4. Like this. Like this. Okay. All right. This one will be correct. 15 will be so 1, 2, 3, 4, 5, 6. You put it in sequentially. This is the correct way for gray code. You see 12. The value of 12. 12 in gray code. In gray code is what? Is 10. So you can see here 10. Hey, wait. 12 is 10 here. How do I put it? 10 will refer to 12. 10 here is 15. 10 here, you see 10 here will refer to 12. 12 here refer to 10. Okay, so this is in gray code format. It looks like this. Okay. All right. Then you have this code converter. All right. You build the care map. Okay. You have the truth table here, isn't it? From this truth table, there's 4 Boolean function. So from this 4 Boolean function, you build the care map, get the Boolean function formula, then build the circuit. So this is a circuit for 4 binary bit to gray code converter. Okay. Then over here, for gray code to binary, so this is the gray code. All right. So hey, there's something wrong here with the gray code here. This is not a gray code. This is not a gray code. Huh? This is not a gray code. Wait. Yeah. This is the gray code. All right. This is a gray code. Okay. Gray code. This one, 4-bit to binary to gray code. Then you have this one, gray code to binary. This is not the sequence of the gray code. This is not the gray code sequence. All right. This one, you get this table from here. Okay, you get this table from here. Because this is not in this format, so you rearrange it. Once you rearrange it, you get back this one. Okay. All right. Okay, so you see here 1010, which is in gray code, it represents the binary value of 12. Okay. Binary value of 12. Okay. Clear? So they rearrange it, so therefore you see like this. Okay. This one, in actual fact, if it's sequentially, it is not a gray code. Okay. All right. This one is a gray code. You can see here, only 1 bit change at one time. All right. All right. Only 1 bit will change because you need to build the truth table. So you have to rearrange this one. Therefore, it becomes like this. All right. Okay. So I hope you can understand. Then once you have the truth table, you have 4 functions, 4 output, that means 4 functions. So from here, you get the output, get the truth table, get the care map, build it, get the function, and this is the circuit. Okay, this is a logic diagram. Okay, so this is a logic diagram for binary to gray, gray to binary. Okay. Then you also have what you call access tree. Access tree, what is the meaning of access? Access means extra 3. So you have a binary number, you plus 3, and only valid from 0 to 7 to 9. Okay? It's actually a BCD to access tree. So you have this BCD code. Anything there's more than 9 is X, you don't care. So whatever value here, you're going to add 3 to it. 0 plus 3 will become 3. 1 plus 3 is 4. 2 plus 3 will be 5, and so on. So you get this. So you have 4 Boolean function. Then you build the care map. Okay. Simplify the function. Then you build the circuit, and you get the circuit. This is the logic diagram. Okay. The next thing is Parity Generator. So in Parity Generator, is used for high-speed thing, like a hard disk, like network card, all right? You need to do error checking and correction. So it has to be done there itself, all right? So the hard disk error checking has to be done at the hard disk itself, by the hard disk itself. So actually it uses hardware to do. So it's a high-speed thing. So you have a 3-bit generator, construct a 3-bit parity generator and a 4-bit. So we're going to do only the 3-bit. So, right? So this parity bit, you can read by yourself, this one. Help yourself, especially this Unhu style. Okay? All right. So you can see here, this is even parity. So the number of 1 has to be even. Okay? Either 0 or even. So there's 2. There's this one also 2, 2. This one is 4. So you can see here, this is a circuit for the parity generator. So you can see here 0, 0, 1. So how many ones are here? Only 1, 1. So you add another 1. Okay. So if the number of bits is odd, you add another 1. If the number of bits is even, you add 0. Okay. So you get this parity function, parity bit. Okay. Then you draw the care map. All right. Then you get the circuit. Okay. All right. Then how about construct a 3-bit odd parity generator? So 3-bit odd parity generator, you can see 0, 0, 0. The number of 1 is what? Number of ones. How many number of 1 is even? So you add 1. So 1, 1, 1. Number of 1 is 1, so you add 0. Okay, and you get this. So this is a Boolean function. Build the care map. So this is a care map. Okay, and you build it, and you get the circuit. It's the same like this one, except you add an inverter in front. Okay, you add an inverter in front. Okay, so that is all these combinatory circuit. Okay, any questions so far? Any questions so far? Any questions so far? No, Okay, now we go to the tutorial. Okay, can you see the slide? Right? Can you see the slides? Can or cannot? Yeah. All right. So you have tutorial 3. I did put it in the PowerPoint. So identify the Boolean expression gives the truth table, okay, for a given logic diagram. So here is A, then here is A bar, C bar, then the output here will be A bar, C bar, bracket bar, okay. Then over here this B bar, so the end of this will be this one. Then the end of these two will be this one, okay. Then over here is AB, then here is ABC, so it's ABC. Added all together, you get this formula lah. Very difficult to express. Okay, they say that use Boolean law, so you cannot use K-map. Draw the truth table. So you have here. So this one you use De Morgan's law, where Nand Gate is equals to negative OR gate. So this one is equals to A bar plus B bar. So thus this one will equals to A double bar and C double bar equals to A plus C. Okay? So therefore this one is equals to this one. You simplify, you get A B bar plus C. Then you can draw the circuit. So this is C. This is the circuit for X. Okay? Then from here, you get the truth table. So you have B bar plus C. B bar is what? All 1 plus C is this one. Then you have A times B bar plus C. So you get this one. Okay? All right. So this is what is the simplified one. Okay, this is the simplified formula. Okay, and this is the merge cell. Can you see merge cell? This is the initial circuit formula. Okay. You see ABC is this one. Then you have this one. You get this one. Then you add it together. You get this one, which is the same. Okay, same. That means that this one is the same. Bold, underline, italic, bold, underline, italic. Okay, same. All right, same. That means that it's proven. Okay. So this is question 1. Question 2. Obtain the sum of the product. So this one, what you do? You change this NAND gate to negative OR gate, these 3. You can see, I changed it already. So in the end, after that, you can see the bubble cancel off each other. You remove the bubble already. So it become like this. Then this one, it can be removed. So it become like this. So the function is FAB plus CD. Then you draw the truth table. This is the truth table. Okay. That's it for the tutorial 3. Okay. Now, any question?
Can I see the question 1, sir?
Question 1. This question 1. I did it in PowerPoint because Word difficult to write, PDF difficult to write. So in the first tutorial, we changed software from PDF to Word, then to PowerPoint. In the third tutorial, everything is speed up, straight to the point. Okay. I upload this in MMLS lah. Okay. Okay not? Okay not? Upload it now lah. Yeah. Yeah. Where should I put it in? Tutorial lah. Okay. Turn on. Okay. And tutorial. Okay. So this is what? Tutorial 3, isn't it? Question 1 and question 2. Explanation. Okay. As attached. Then all the LO is there. Wow. Tutorial. Okay. Done. Already uploaded. You can get it from there. Okay. All right. Okay. Now let's do session tutorial lecture 4. Okay. Can you all see the slide? Lecture 4. Can or not? Can, huh? So we're going to talk about, this is the coverage for lecture 4. We're going to go through briefly lah. Okay, we explain things that we further explain the things so that you can further understand your lecture. So you have initially what you learn is combinatory circuit. You have output is a function of an input. So the input you process with a Boolean function, you get the output. There's no memory element. There's no storage. Okay, you cannot remember anything. Okay, so but memory is required for many systems. It requires like traffic light, ever later, coin vending machine, parking lot, or parking slot machine, parking meter. All these require state. Okay, like a traffic light. You need to know currently, you need to remember what is a light at the junction, whether it's a red, green, or yellow. All right, you need to remember the previous state. All right. Then for ever later, you need to know that which floor are you in, all right? Whether the door is open or closed, whether the lift is moving or stop, all right? You need to know that, okay? So you need to keep memory. Okay, the coin vending machine, you need to know how many coins has been put into it, okay? Like a parking meter machine, you need to know that whether it's a 1 ringgit or 10 ringgit, then whether you need to how much change you need to give, all right? All that, all these require memory, okay? So you have this introduction, you have asynchronous and synchronous circuit. All right, so this is how it looks like. You still have the combinatory circuit, you still need it, all right? You have the input, go to the combinatory circuit, give an output, and the output of the combinatory circuit will be stored in the memory element. Let's say you have a timer in the traffic light system, you have a timer. After the timer, you have an external input from the timer. Then you can see the next state is red, so the red will be stored here. Okay, the present state is yellow, you put feedback as an input. Okay, the present state will be feedback to the combinatory circuit as input. All right, so this is generally how it looks like in a sequential logic circuit. Question. Any question? Let me see the chat. Okay, clear, crystal clear. Okay. All right. Okay. So you have two. One is asynchronous and synchronous. Asynchronous basically are latches. Synchronous are basically are flip-flop. So in synchronous, asynchronous, when the input change, the output change immediately. Right? When you change the input, the output will change immediately. Okay. Whereas in the synchronous, basically when you change the input, the output does not change until the next clock pulse. Okay. So the clock provides some form of stability. All right. Okay. So this one is a synchronous. You have a flip-flop that provide a clock pulse and the timing diagram of the pulse. So what will happen is that if there's two input A and Q, you want to change A and Q at the same time is difficult because it's electronic. There will be some delay. There will be some delay. A change first or Q change first. You cannot control, right? maybe at low speed you can control, but at a high speed, definitely you cannot control. Okay, because in physics, nothing come at the same time. Okay, so you have to have a race condition. Sometimes you lead to unstable circuit. Okay, so you have to wait for A and B to be stable first. So you use a clock. The clock is something like a waiting device lah. Okay. Once the clock, so every clock pulse it will trigger. Right? The purpose of the clock is to stabilize the input. So you make sure all the input, all the changes have been changed. Then only the output is calculated. Okay, so you have the latches, you have the Nand Gate, NOR Gate, SR latches, and so on. Okay, so these are the gates. Latches with surface flop. So latches will change the state immediately. Flip-flop will wait for the clock signal. Okay, basically flip-flop is a latches, but we have an extra clock input. Okay, so both of them have two stable state. All right, stable state means 0 or 1. Stable state. Okay, so these are latches. So you can have the input, and you have a normal output and an inverted output. Okay, so the normal output Q equals to high. So when Q equals to 1 is a set. When clear is equals to 1 is reset. All right. So you have SR, set and reset. Okay. So this is a basic SR latches. Okay. Basic SR latches. You can see this is using Nand Gate. So this is active low. So in active low, you have S bar and R bar. Okay. Connected. The output is connected back as an input. Therefore, it has provide the stability. Okay, so this is a truth table. So when it is 1, 1, when S and R is S bar and R bar is 1, 1, so there's no change. Right? If it's 0, 1, the output will be set to 1, 0. If it's 1, 0, the output will set to 0, 1. If it's 0, 0, it is in the invalid condition. Okay, so okay, so this is because this one is using a Nand gate, so it's an active low. Okay, so this SR latches using active low. Okay, okay. So in the SR latches, when you change the set here, there's no change because the condition is 0. Okay. So when you set is 0, clear is 1, so the output should be 1. So you can change, you can see the changes immediately happen. Okay. The same thing goes to here. When clear is 0, set is 1, output should be 0. So you can see here, the changes immediately happen. Okay. Once you change the output, the input, the output changes immediately. Okay. Then you also have a SR latch using a NOR gate. Okay. So let me stop sharing for a while. So wait a minute. Let's continue. So in the SR latches using a NOR gate, it's the opposite. It's slightly different from Nand gate. So this is active high. So you can see 0, 0, there's no change. 0, 0, there's no change. Compared to here, you can see 1, 1, there's no change. Because this is S bar and R bar. So over here is S, R and S, all right? So you can see here, like this is 1, 1, there's no 1, 1 is forbidden. 1, 0, if the set is 1, R is 0, so that means the output will be 1. If the reset is 1, then the output will be 0. Okay? So let me stop sharing and share the whole screen. every NAND gate is it active low? I would say generally yes lah. Generally yes lah. In chips lah. Okay. Generally yes lah. Okay, but okay. Okay, let me open up the application. Okay. Where is it? Teaching. App, digital works. Okay. Okay, opening the application. All right. Now, okay. So you can see, can you see the digital works that I share? Can you see? The digital works. Okay, so you can see this NAND gate. All right. So you must see the position. S is down here. This one S is up here. So you can see this 0, 0 and 1, 1. This is a unstable state. 0, 0 is unstable state. 1, 1 is unstable state because this is Q. This is Q bar. All right. So both of them must be different. So let's say you put in this one is an active high. You put set equals to okay, set equals to 1. So Q will be 1. Okay. So put here Q and put here okay, Q here. And over here Q bar. Okay, you can see here. Okay. So set equals to 1, but this is, let me change edit. So this is S bar actually. And this is R bar actually. Okay. So indeed S bar equals to 0 and this equals to 1. You get the same thing. Okay. So when this one 1, 1, that means this one is 0, 0. Okay. There's no change. Okay. And this one is 0. All right. Okay. So this is active low. This is active high. Okay. All right. Clear? Clear. Any question? Any questions so far? So this Sr Latches, you can do it using a digital works. Okay. So only in the early 80s, early 90s, late 90s, you have this software. Late 90s, I would say. Late 90s. Right? Late 90s, 1998, you know. Not sure when is it. Okay. But before this, so what happened is that you have to build, during my time, you have to build the circuit by yourself. Right? You cannot verify using software. Right? You cannot verify using software. Right? Of course, there is software available, but might be too expensive at the time or what. Okay? During the early 90s. Right? If you build your circuit wrongly and all your circuit diagram, all your wiring wrongly, you go to the lab, doesn't work the way you want, then you see, check. Oh, something is wrong with your design. Then your whole lab is gone, man. I can tell you. There'll not enough time for you to rewire everything. All right. So you have to triple check everything before you go to the lab. Okay, that was in the 90s lah, early 90s lah. But in the late 90s, you have this software. So what you do is that you design everything, you check the software. If it's correct, simulated correctly, then you can confidently go to the lab and work it out. Okay? Then it's just a matter of wiring or chip error or anything. Okay? Clear? Okay, let's go back to the slide. Okay, so these SR latches. Okay. So you can also see it changed immediately when the input change. It changed immediately. Okay, so then you want to have a gated. So what you do, you want to have a what you call enable pin. So when you have an enable pin, all right, only when it's enabled, then only you can. When this enable equals to 1, only the output will change. Okay, so this is enable pin. So you can see here, this is one of the SR latches. When C equals to 1, what will happen? The input here will be S. The input here will be R, isn't it? Okay, so if it's R, then the Q will be, and the Q bar will depend on the SR value. But if it's C is 0, what will happen? So this one will be the S here will be 0. And over here, M will be 0. So based on the truth table, what is 0, 0? No change. 0, 0, no change. Okay? So in order for you to have change, you have this enable pin. All right? You have an enable pin here. Okay? So let's see the circuit. It's like this, enable. Okay? So you can see here, this is active. So when you enable, when you put enable it, okay, then there will be changes. Okay, okay, okay. You can see there will be changes. Okay, only when the enable, when it's disabled, you won't be have any changes. Okay, so this enable pin. Okay. All right. So this is the truth table. So normally in any flip-flop or latches, you have this C. C is enable. Okay. C is the enable pin to enable the latches. Okay. So only when the enable pin is on, then only the changes will happen. Okay. So then you also have what you call D latch. So in the SR NOR gate, you cannot have S equals to 1 and R equals to 1, isn't it? So you have a D flip-flop, meaning that the input go to S and there's an inverter go to R. So in this case, S and R equals to 1, 1 will not be possible in the D flip-flop. Okay? So in the D flip-flop, very easy. If you input 1, the flip-flop will be 1. If you input 0, the flip-flop will be 0. Okay? So very straightforward D flip-flop. Okay? Then you also have gate latches, D latches, okay? Using NOR and AND gate and inverter. Okay? So this is the truth table for gate or gated D latches. Okay. Then you have a flip-flop. In a flip-flop, you have two things. One is a positive edge trigger and negative edge trigger. Okay. Positive edge trigger is a is the pulse that going from 0 to 1. Negative H means that from 1 to 0. So you can see here in the clock symbol, positive H, so from 0 to 1. So you can see here there's no bubble. If a negative H trigger, there's a bubble here from 1 to 0, okay? From 1 to 0, okay? Okay. How does it change, all right? Because there's an inverter here. So when it's from 1 to 0, it becomes 0 to 1, okay? Over inside the clock, okay? So you have set, reset, set, clear. Okay, wait. So you have a positive H trigger. So when you can see here the positive H trigger, so you can see here the clock arrow is moving up. Okay, if it's a negative H trigger, it's moving down. Okay, all right. So you can see here when S and R changes, all right, there's no change. All right. So when the changes only happen here, you can see when you are set, when there's a clock pulse and it's going up, the same thing goes to here and to here. Okay. All right. Okay, the changes will only happen when there's a clock pulse. Okay, when there's a clock pulse. First, you change the input, then you wait for the clock pulse, then the output will change. Okay, so it's based on clock pulse. Then you can see here in the negative H trigger, the arrow is going down in the table. The arrow is going down. Okay. All right. All right. So from here you have a H detector. Okay. You go. This is the clock pulse. Okay. Okay. This one is you can skip this. I don't think it's that important. Okay. Then you have what you call a JK flip flop. So what's a JK flip flop? So you know that in SR flip flop 1 is invalid, so it lead to unstable state. So flip flop is a basic unit in every circuit. Many circuit that require memory, you require flip flop. You put something 1 invalid, all right? Then it's a pain in the ass, all right? So something very basic, you should not let that happen. So remove that. So then you come up with a JK equals to 1, 1. That means that the input will toggle, okay? So it's much more versatile, all right? How does toggling is versatile? Okay. Okay, let's say in SR flip flop, you want Q from X. X means that it's either 0 or 1. You want it to become 1, so you set it to 1. Right? In D flip flop, you want D to become 1. Okay, you set D to become 1. Let's say if you Q X, you want 0, so you set SR to 0, but in D flip flop, you set D equals to 0. But what if you want Q equals to Q bar? So in SR flip flop, in D flip flop, you have to change the input. You have to compare state. Work, isn't it? So in JK flip flop, very easy. You just set JK to 1, 1. Then Q will become Q bar in the next clock cycle. Okay, easy. You don't have to change the input. Okay. The actually not to say don't have to change. The input is this bracket is connected to the output, the Q output Q, okay, which you do in the later design. Okay. So this is a JK flip flop. This is a negative H trigger. How do you do a negative H trigger? So this is from 0 to 1, isn't it? Okay, from 1 to 0, isn't it? From 1 to 0, isn't it? here is 0, okay? From 1 to 0. Okay, from 1 to 0. Okay, so you go through an inverter. So then this one will become from 0 to 1. It will become from, then what actually happened, it become right here lah. It become 0 to 1. Right, draw an arrow. Okay, because you go through inverter, it's from 0 to 1, then there will be a trigger lah. Okay, but this one, that's how you do the negative edge trigger. Okay, you can see here, the clock is negative edge lah. Okay. All right. So this is the logic diagram. Then you can have a D flip-flop. You can change the D flip-flop from the JK flip-flop. Just put a D, then put an inverter here on the K part. The D connected to the J, the inverted of the D connected to the K. This is how you change the JK flip-flop to a D flip-flop. Okay. Then you have a T flip-flop. T flip-flop is a toggle. What do you mean by toggle? Toggle means back and forth lah. Okay, it means back and forth. Okay, so if you change T equals to 0, there's no change. If you think T equals to 1, that means that JK equals to 1, 1. That means that it will input, the signal will input to each other. Okay. Okay, this is how you implement a T flip-flop. Okay, you have a D flip-flop, come up with an exclusive OR with a T here, then you become a you become a T flip-flop. Okay, from D flip-flop become a T flip-flop is like this. From JK become a T is used like this. Okay, then you have the characteristic table. Okay, excitation table. So this one you have to remember. If you want 0 to 0, that means that currently is 0. You want the next one to be 0, you put S is 0. Okay, just put S is 0. If you want currently is 0, you want it to be 1, you put 1, 0. Okay, in SR flip-flop. If you want 1, currently is 1, you want it to be 0, you put set equals to 0, reset equals to 1. If it's 1, 1, no change, then you just put R equals to 0. Okay. All right. So in D flip-flop is straightforward. You want the next state to be 0, you put 0. You want the next state to be 1, you put 1. Okay. In the T flip-flop, if you want, so this is the excitation table. The only part that is difficult to remember is the JK part. Okay. You need to remember this. Before, this is important when you want to do a memory circuit design. Okay. Then you have an asynchronous input. This is how an asynchronous input looks like. Okay, asynchronous input. What is this all about? What is this all about? Asynchronous. What's the meaning of asynchronous? Asynchronous means immediately. Okay. Okay. Asynchronous input means immediately. So sometimes you have let's say you have 1 bit memory lah. Okay. So when you power on the machine, power on the circuit, what is the value in the flip-flop? What's the value in the flip-flop? It can be 0 or 1. You won't know. Right? Okay. So before you, right? So before anything, you need to initialize the circuit. How do you initialize it? So you have to manually set the value into the flip-flop. So therefore you have this asynchronous input. Okay, are you clear? You have this asynchronous input. So you can see here. So you can see here is a preset and cleared. So this is the asynchronous input. Preset means that you preset, okay, and clear. All right. If it's 1 1, it will be 0. All right. You need to look at the table. If it's clear, right? You have the Q value. Okay. So because this is inverted, preset means that you set the value. So you have two values here. Preset and clear, inverted. Okay. So if preset is 0, because this is a preset bar, if the preset is 0, then it will be 1. Okay. If the clear is 0, then it will be 0. Okay. All right. So this one will allow you to manually, okay, this allow you to manually load the value into memory. So example like a traffic light. So initial condition. What's the initial condition? Should be all red lah. Okay, everything red lah. Okay. All right. What happens? You put all green, then there will be accident. All right. Okay. So that's the rationale of the asynchronous input. So in any memory chip, you have this preset, and clear. Okay, you can see it. Okay. Sometimes it gets tricky whether it's a negative-ish preset is negative, all right, or positive, all right. Okay. Okay, so there's a application of a flip-flop. It can be store binary data, all right, transfer binary data, and so on. Many applications. Okay, so you can transfer data, parallel transfer, transfer data to a CPU to a register, and then you have this finite state machine. Finite state machine is for you to do like a coin vending machine. This is all finite state machine. Finite, what do you mean by finite? What do you mean by finite? Finite state machine, example like a traffic light. Right? How many states? You have red, green, yellow. Okay. Okay. So you have 3 states. So 3 is equal to finite. So 3 states, how many bits you need? You need 2 to the power of 2 bits. Right? So it become 4 states, isn't it? So there's 1 invalid state. Okay. You learn that in the finite state machine design. Okay. Then you can build the circuit out of it. Okay. And then after Lee, right? And EF Morrow. Okay. So this is a finite state machine. Okay. Okay, I'm done. Okay, any question? Do we need to remember for logic circuit? I think you should. I think you should because it's the basic element in computing and in E&E, electrical engineering. Right? basic element. Okay, basic element. Okay, so should remember. At least you should remember. Just very easy, Nima. Just very easy how to remember. All right, you just two Nand Gate, right? Then the input feedback to the output feedback to the input lah. Output feedback to the input. Right? Cross feedback. Right? Or it can be a two NOR gates. All right. You can see here. Where is it? This one cannot remember. Okay, cannot remember. Oh, you can remember. Okay. Maybe I don't expect you when you go out and do sales. All right. I don't expect you to remember lah, but in your lifespan, you should be able to recall quickly lah. Okay. That is minimum expectation lah. Okay. I don't expect you to remember until you dead lah. But then if in time of crisis where you need to remember, you should be able to recall quickly, all right? Go through the books, right? Or my YouTube channel, at least, all right? Then you read my YouTube channel, listen, or then you recall already, okay? So how do you make sure that you really recall? So you must like, share, and subscribe, all right? Okay? All right, so I think I finished, I stopped recording now. Okay. All right, I stopped the recording now, and this is a fantastic tutorial. So I will upload it, all right, for this tutorial.